term. It is interesting, but of course these terms are going to be less important for a dilute gas. Third, terms of the order of 1 over 3 lambda t cube, t to the power 6. If lambda t is small, that is quite large, but the integral is a double integral, 0, 8, so infinity from 0 to infinity, f(1,2), f(1,3), f(2,3), d cube r(1,2), d cube r(1,3). And that's the way it goes. You can read your book or other sources about this virial expansion. This last term A3 can correspond to a 3 cluster. One, two, three. So that's the contact between this expansion and the cluster expansion. Now, I will consider really dilute gas so that you need to keep only the 2 terms. You don't have to go to that term. Okay? And calculate these quantities and see what it gives us. Do we expect anything for the equation of state, for example, for this type of a gas? You don't expect anything. You should expect something. Okay, let's calculate and then speak. Probably that's a better approach. Dilute gas, very small deviation from ideal gas, enough to keep 2 virial coefficients, and try to calculate these only and see their effect on the equation of state. If you write the integral explicitly, d cube r is 4 pi r squared dr, isn't it? Nothing depends on angles. So you have this result for the first 2 coefficients. Now, of course, we need a model for potential energy of interaction between particles, U, I, J, pair interaction. And one model is Lennard-Jones potential. Let's assume you are of this form. This is coming from 1924's. The potential has this form. This is also known as 612 potential, referring to powers of R, 1 over R, isn't it? This term corresponds to what? Attraction or repulsion? Repulsion is positive. That's the negative term, that's the repulsion, attraction, sorry. Okay? So, with this potential, whose minimum is epsilon, minus epsilon, at a distance r0, 2 to the power 1 over 6 sigma, okay? Take derivative, put equal to 0, and find r. Well, it is like infinity for r smaller than sigma. It is the repulsive part. It is like 0 for r very much greater than sigma, isn't it? So it goes to 0 when the interparticle distance is large. So for practical purposes then, we can approximate UR as plus infinity for r smaller than r0, and it is minus u0 r0 over r to the point 6 for r very much greater than r0. So that is the model that we are going to use for you all. To make the calculation simple, that's what I'm going to do, and calculate the second virial question. It's a nice problem, isn't it? UR is given, calculate the second virial coefficient, this quantity. We know the first one. So what you are going to calculate is 2 pi lambda t cubed. If you, well, you can divide this integral into two regions from 0 to r0 and r0 to infinity. Okay, Gesundheit. Divide it into two. In one, when you take it to be plus infinity, this is 0. So you end up with an integral like this. And the other part from r0 to infinity, it is 1 minus e to the, well, ur over kbt r squared dr, isn't it? So you can do that integral rather easily. What should you do to do the integral easily? Tell me. You expand the exponential, isn't it? UR is going to 0 for large R, so you can expand that into exponential for large R. So the result will be 2 pi. Exponential is 1 plus UR over kBt squared, 1 plus UR if you like, 2 pi R0 cube, 3 lambda t cube. Check this. I'm not guaranteeing anything. 1 minus u0 over kbt. So all you have to do is to expand this as 1 plus u0 over kbt r0 over r to the power 6. Okay? So ones will cancel, so you end up with a simple integral. Well, if you substitute this result into equation of state expansion, here is the form you obtain for the equation of state. Substitute back equation of state, so you end up with PV kbt is 1 plus A2 lambda t cube over B. We are going to see the first effect of interaction. This turns out to be 1 plus 2 pi r0 cube over 3v 1 minus u0 over kbt. Well, sometimes this coefficient is called, where you can write the whole thing as P equals kbt over V okay, I think that's correct. 1 plus 2 pi r0 cube over 3v 1 minus u0 over kbt. As I am always telling you, check this, do the calculation yourself. In some books, the coefficient is written a little bit differently. That term is written as kbt over V 1 plus B2T over V. And this is called the second virial coefficient, not A2, but B2 is called second virial coefficient. Depends on the book you use. B2T is A2 times lambda T cube. That's the relationship. Sometimes that is called a second virial coefficient. Okay, well, we have a corrected form for the equation of state. It is no longer PV equals NKBT, isn't it? There's a correction term, and correction term depends on temperature. The equation of state changed effectively. You can rewrite this in the form, if you like, P plus 2 pi R0 cube U0 divided by 3V squared equals more or less as kBt over b 1 plus 2 pi r0 cube over 3b, or can be written as kBt over b 1 minus 2 pi r0 cube over 3b to the power minus 1. And this way of writing it gives us almost the form of van der Waals equation. I hope you heard about it. So, equation of state has changed into the van der Waals form or approximation. Which has this form. Where they have found that A is 2 pi r0 cube u0 over 3 and B 2 pi r0 cube over 3 over 4 v0. Here we have assumed that B is very much smaller than B. Which means that the gas is dilute as this means that mean interparticle distance is much larger than the interparticle maximum or minimum of the interparticle interaction, where the interaction is the most effective. In other words, they interact with very low, very small potential energy. Have you seen this van der Waals before? Huh? Of course, probably in high school. Huh? So you don't remember anything. What does that mean? Well, it includes the interaction, effect of interaction between particles. Where is the attraction and repulsion in this equation? Well, it looks like effective volume is reduced. What type of, which part of the interaction it comes from? Attraction or repulsion? Not the whole volume is available to the particles, but some volume is not reachable because particles are repelling each other. If there's a repulsion, the particle cannot penetrate into a region where repulsion is maximum, isn't it? No penetration means some volume is excluded volume, isn't it? Is not available to the particle. Like hard spheres. So this volume being decreased is coming from repulsive part of the interaction. And that is P plus. That means pressure is being reduced, isn't it? When you write pressure, there's a negative term on the other side. So why should pressure be reduced? Because of attraction between particles. Can you give me a rough general physics type of explanation for this? You are so silent today. It's not good for physics. Well, if the particles are attracting each other, imagine a particle going to the wall and having a collision with it, because the pressure is momentum exchange with the wall, isn't it? Change in momentum. But if something is pulling it back, that momentum exchange will be not so effective, isn't it? So pressure will be reduced. Why don't you think like a physicist? You should think like a physicist, I think. You are trying to be a physicist, aren't you? So why don't you think at all then? Well, I know you are thinking. It takes a little bit longer to see what's going on and interpret everything in physics terms. So we have discovered one result of interaction between particles. We no longer have PV equals NKVT. That equation of state has changed. It has the effect of attraction between particles and repulsion between particles. So both parts of the potential contribute to reduce the pressure and reduce the volume available to particles because of the repulsion between particles. So particles cannot penetrate into some of the volume, may call it exclusion volume. Now let's see a little bit more what happens with interactions. This part is going to have a contact with the experiment, okay? The question is, what happens to the structure of the system? Where are these atoms? Where are these particles in space? Is there a correlation between positions of particles? Do you know what I mean by correlation? We understood this result of interaction between particles, equation of state changes, it is written as an expansion, etc. Okay. But now the question is the interaction between particles cause a special distribution of particles in space? That means the positions being correlated. It should be obvious. The reason is, if they are not interacting, the position of one, presence of one, will not affect the presence of others. They are not seeing each other. So they are not going to have a correlation in their position because they don't see each other, no interaction. But if there is an interaction, then of course, if you put one here, the other one will have the effect of this presence of this, the first particle. If you put a third one, fourth one, fifth one, creating the whole system, particles will have correlations between their positions. They are no longer completely random, isn't it? Now, so what we can write here is that interparticle interactions cause correlations. Let's write that. Interparticle interactions cause correlations. In the position of particles. They are no longer completely random. In a gas, particles are completely random. They can be anywhere they like. There is no correlation between positions of particles. But here, there must be a correlation. Well, in a dilute gas, we don't have a strong correlation, weak interaction. But if we want to look at a liquid or a solid, of course, positions of particles are not random. Usually we have crystallines, solids. In crystals, there is a perfect order in the system. You know, if you look to the structure from the position of one atom, you see exactly where the next neighbors are and next nearest neighbors are. So you have shells of particles around that, isn't it? At exact positions. We call that long-range order. But if you go into a liquid, sit on an atom, imagine that you are looking around and trying to see where the other particles are. Well, first neighbors can feel the presence of this, and they are correlated. Second neighbors may be correlated, but you lose it as you go away from this particle, isn't it? So we have a short-range correlation in the case of a liquid. Long-range order in crystal, short-range order in liquid, and close to randomness in the gas case. Extremely important. So the structure of the system is determined by interactions. For example, if I tell you that a crystal has FCC structure, face-centered cubic structure or simple cubic structure, what am I saying? Why do you think you have that structure in the crystal? That the atoms are sitting at certain perfect symmetry points. Why some other crystals have, for example, body-centered cubic structure? What can you think about this? Simply because the total energy is minimum in those structures. If you have a certain type of atom, try to make a solid out of it by lowering the temperature, increasing the pressure. They go into a very specific structure, and in that structure, for those atoms, you have a minimum energy configuration. Okay. Now let's describe these correlations with some mathematical terms. First, let me summarize what I said. Particles means atoms and molecules, right? Depending on the structure you are talking about. So, low density vapor had nearly uncorrelated, isn't it? If there is an order, it must be a very short range order. Liquids dense liquid strong correlation, but these are decaying very quickly at large distances, short range order in other words. Did you know that liquids had some order at all? Huh? You didn't. You don't even know what I'm talking about. No, it makes sense, isn't it? The interparticle distance between particles in the liquid and solid are more or less equal, isn't it? They're dense, both of them. Crystal solids, again strong correlations and long range order. Here correlations decay. Here correlations don't decay. Here they decay exponentially. After two neighbors, you don't have any order. Well, these facts, where the atoms or molecules are sitting, can be described by spatial correlation functions. And these are based on n-particle densities. Based on n-particle densities. One particle number density or one body number density can be written as N1 R, and it is defined as, interesting, R minus Ri. There is a contribution if R equals Ri at the particle. The meaning of this function is that N1 R dr, you can also write this as d cube R, infinitesimal volume. Now I write the meaning of this function. This is a measure of probability of finding a particle in dr at the position R. This is extremely important function, I think, correlation functions. And their definition will take us to the experiment in finding the structure of your system, where the atoms are sitting. So it is the probability of finding a particle in an infinitesimal volume element, d cube R, at position R. Okay? This is one-body number density. Now let's go to two-body pair distribution. But before going to that problem, what happens to N1 if the density is uniform? If, before that, let's go to translationally invariant system. Invariant. If there is an invariance, translational invariance, almost uniform, you have N1 as a constant, isn't it? This is the probability of finding a particle at any position, isn't it? Number density itself. Number of particles per unit volume. That's the number density. Is that okay? Good. So the integral of N1R dr is average number of particles in the system. If n is constant, you have volume. Integral gives you volume, isn't it? So this is if translationally invariant, means equally probable to find the system in anywhere. Now let's go to two-particle, two-body number density. Well, this quantity, R prime, as you can imagine, it is the probability of finding one of the particles at R, when it is at R, what is the probability of finding a second particle at R prime? So it is defined as an average of I different than J delta R I delta R prime R J. That's the definition of the correlation function. Two-body number density. So this is a measure of probability of finding one particle in volume dr at R, another in dr prime at R prime. Okay, extremely important. You can write N2 R prime as N1 at R and 1 at R prime as the interparticle distance goes to infinity. They are very much separated. We have that relation with one body densities. One important property of this function is that it gives the following result. If you integrate that, you get n squared minus n squared. Check that, okay? Check that. Now, if we have a system which is both translationally and rotationally invariant, if system is both translationally and rotationally invariant, okay. N1 will be independent of position, N2 depends only on magnitude between distance between R and R prime, something like this. Well, in this case, we are allowed to define a pair correlation function, which is available to experiment, extremely important. allows us to define a pair correlation function. Now we are finally at a quantity which can be measured in an experiment. Can define pair correlation function which is known as G of R, and the definition is as follows: N2 or R prime is N squared G R minus R prime, magnitude of the distance between the particles. Well, if you have a three-dimensional system, the meaning of this GR, as I'm going to finish this, 4 pi n r squared gr dr means exactly probability of finding a particle in a spherical shell of radius r, thickness dr, given that another particle is at origin. Is that clear? Four pi n r squared dr, gr multiplied by that. Well, 4 pi r squared dr is the volume of the spherical shell, isn't it? If you multiply it with n gr, you get probability of finding the second particle in a spherical shell at r, of radius r, when the other particle is at origin. This function contains everything about the structure of the system, the positions of atoms. So if we know this function, more or less we know what is the structure of the system. Atomic structure, I mean, isn't it? Where are the atoms? What is the probability of finding a second particle at a certain distance if the one is at origin? Huh? And these can be measured experimentally. I will give you explicit forms of this function next lecture, okay?